Official members bounce, bust off the chrome. Realize it's real hell where we call home.
Official members bounce, bust off the chrome. Realize it's real hell where we call home.
From the heart inside one, I vision fat licks and mat clips. The chroma make the average imitator do backflips. You lack a pistol, so put a vest around the issue. Slugs will never miss you. Coming from members, that's official.
Okay, we have 3 lectures left. So for you guys in the class, the roadmap to finish up the semester, we're almost there. We have no class, obviously, that should be Wednesday, not Thursday. This Thursday's Thanksgiving. Wednesdays, there's no class on campus or the university, so don't show up here. I still will hold my office hours. I'll post it on Slack, or not Slack, post it on Piazza. We'll do it over Zoom. So if you want to talk to me on Wednesday, I'll still hold my regular office hours, even though we're not having a lecture. The Wednesday's class next week, at the end of the semester, we typically do this potpourri session where in the past we've had students vote for what systems they want me to cover. So it's like flash talks from Andy. Like I'll try to cover as many database systems as I can in like 5 minutes. We can do real ones, we can do fake ones, we can do hobby ones or joke ones, parody ones, like MongoDB instead of MongoDB, right? Things like that. Or we could do if there's a bunch of topics you guys want to learn more about, we can cover try to go off the cuff in like 5 minutes, try to cover those. So I'll post on Piazza what we want to do this semester. I'm up for anything. You guys can vote for what you want to do. In previous lectures, we've done call-in shows where people like from the outside CMU can call in and ask crazy questions. You guys can ask questions. So we can do anything. So I'll post on, again, Piazza what we want to do. Project 4, we do on the Sunday, December 8th at midnight. Homework 6, I think was the grade scope, it was due December 4th. The website, it was due December 8th. I've changed this now. Gradescope and the website now, giving you an extra day. It'll be due on December 9th. Okay? Yes?
Can we use grace days on Project 4?
Can you use late days for Project 4? Yeah, why not?
Some classes don't allow us to use grace on
I mean, like, I don't think the university doesn't want anything due the week of finals. But, like, I don't care if you don't care, right? Like... so yeah, you can use late days. I mean, final grades aren't due till like December 18th or something like that, right? There's some date I have to put in final grades. So as long as you get it done before that, I don't care, right? And then the final exam will be December 13th. Again, so we want to get the part of the reason why I'm making this due earlier rather than later because we want to give you the solutions and everything by the 13th. So we'll put them out like maybe the 11th. But the homework 6 isn't there won't be a lot of topics covered in homework 6 in the final exam because you're not building that, you're not building it for the projects, right? We want to emphasize the things we do in the projects. So again, December 13th, Friday, 8:30 a.m. We'll do the study, the final exam review Wednesday's next class before the potpourri session. But there won't be early exam, and then don't disappear before the date, okay? There's 2 more database talks this semester. Today we have the guys in China doing grepTimeDB. It's a time series database built on Data Fusion. That'll be at 4:30 again on Zoom. And then next week we have another dude for another system in China called DataBend. But they've sort of, in the same way that like Data Fusion was sort of this standalone piece that they built to do query execution, OpenDAL is a data access layer, meaning like think of like the disk manager in BusTub, like you have your buffer pool talk to some disk manager that then goes out to some disk and gets the data. So they have a layer that replaces the disk manager that you can replace the thing in BusTub to go read data from S3, read data from EBS, or whatever remote URL you want. So that guy's going to give a talk. That should be not November 25th, whatever Monday is next week. I think December 2nd or something. Okay? All right, so I wasn't here last class. I was in Chicago. Then I had to go to Amsterdam for an award session, and then my parole officer's all pissed off because, like, whatever. So, because it was out of the country, but even though it was an award session, it wasn't my award, but I was giving a talk at the award. So, like, oh, that doesn't count for work because it's not my award, but like, whatever. All right. So that was last week. So I apologize for not being here, but Wan did a good job. So last class, Wan talked about again the introduction to distributed databases. And he presented these sort of the basic 3 system architectures that you can have in a database system. Shared everything is what we understand bus hub or something like PostgreSDB, right, where it's like a single system that's running on a single box that has control of the disk, the memory, and the CPU, and everything's all local to it. The shared disk architecture is where something is like running on S3, or there's this distributed file system layer where you have multiple compute nodes that essentially aren't holding the data, but know how to access that shared storage to go pull the data out and do something with it. And then shared nothing is the classic distributed system where every node is a sort of holds a piece of the data that is in your database. And anytime you want to run queries or transactions across them, right, you're sending messages between those nodes, and they know how to talk between them, right? So before the cloud, before something like S3 and the prominence of that, shared nothing was the most common distributed system approach, and shared disk was actually considered a bad idea because Oracle tried it and Teradata tried it. It was always kind of expensive, but like with S3, that's a game changer, right? Snowflake was one of the first systems that came along and said, hey, let's build on a shared disk architecture on top of S3 so we don't have to do storage ourselves. And that was a huge win for them. Again, so the award ceremony I was at last week was the co-founder of Snowflake. Then we saw different ways to split up the database, right? The partition sharding schemes, hash partitioning, range partitioning. It's just a way to say I have a database. It's larger than I can fit on a single node. How do I split it up and distribute it across my different nodes? And even if you're doing a shared disk architecture, or something like S3 has technically infinite storage, you still need a way to assign what compute nodes are allowed to touch or look at what pieces of data. And a partitioning scheme would give you that. And then he talked a little about, at the end, the different ways you can coordinate transactions. And that's one of the big things we're talking about today is, do I have this sort of global traffic cop that is in charge of deciding what transactions are allowed to commit and when? Or am I doing decentralized architecture where I have the different nodes coordinate amongst themselves of how to commit transactions? Right? And so we're not going to see a real distinction in centralized and decentralized today, but like the protocols we'll talk about today, it actually doesn't matter which one of these two you're doing. So just as a reminder for everyone, what do we mean when we say we're doing OLTP? Right? We had this distinction early in the semester where we talked about OLTP versus OLAP, or online transaction processing versus online analytical processing. Right? The transaction processing world, we're talking about queries that touch a small amount of data, but actually can modify the database. They can update records, insert and delete, and so forth. And they're basically doing the same operations over and over again. But we don't care whether they're doing the same thing over again. The thing we care about is that now they're modifying the database, or now they want to see the database in a consistent state with all the asset properties that we learned about before. And now how do we manage that and coordinate that across multiple nodes? And I realize that I'm only giving you a single lecture. If you count last semester or last class as 2 lectures, like distributed databases, distributed transaction databases are super hard. We could do years on this. I'm just trying to give you a quick brain dump of like, here's the things you got to be aware of. So when you go out in the real world, you can at least be aware of the different things you have to consider. And then Monday's class next week, we'll talk about how to do a distributed OLAP system, right? Basically, how do you do a join across multiple nodes? That's actually really hard. Okay? All right, so if we go back to the diagram we had before from last class, this decentralized coordinator, right? Say we have a transaction that's going to run the application server here. It wants to touch data at these three nodes. And assume we're just doing simple partitions. We have P1 to P4. So we get a begin request. Somehow we know to land on this one node where P1 is located. And we're going to designate that as the primary node of this transaction, right? What that means, we'll see in a second. But then now, assuming that the application server can talk to any other node, it can send query requests to all the other nodes to update things, get some data, do whatever it wants. And then now, and this is all done in the context of a transaction. So then now when my application server says I want to commit, this primary node is responsible for communicating with the other nodes and say, hey, all right, we were all involved in this transaction. Is it safe to commit? Yes or no? And then once they all agree, which we'll talk about how we get that agreement, which is not easy, then we can send the acknowledgement back to the application server and say, yes, your transaction has successfully committed. And again, assuming we're running with all the same asset guarantees that we talked about before on a single node shared everything system, no matter what happens to my database system, if I crash, if any of these nodes crash or the whole thing crashes, come back, I should still see all my data. Or now if I tell the outside world my transaction is committed, if anybody then tries to read data, maybe P3, I should see the changes that I saw that were created by this other transaction, assuming it hasn't been updated yet. So how to actually achieve this is not easy. And very, very hard, and people often get it wrong, and really wrong. And oftentimes in the NoSQL world, they just don't do it because it's hard. So our big idea we're trying to do is what we talked about before, is that we're going to have our database split across multiple resources, so multiple compute nodes, multiple multiple disks, it doesn't matter. But we want them to appear to the outside world, to the application server, as a single logical database system or a single logical database. So we don't care in our SQL code what node is going to run our query. We just say, here's the query we want to run. And so whether our database is split across one machine or 1,000 machines, our SQL query should just work all the same. But things we haven't discussed so far is, what do we do to make sure everyone agrees that a transaction is allowed to commit? And then when it does say go to commit, how do we make sure that it actually gets committed? And again, we come back, we see all our changes. So it's easy when everything's up and running just as fine, right? If there's no failures, no big deal, right? But it's when things start to go bad, and they will in the real world, then things become more challenging. So things we'll talk about today is, what happens if a node fails while we're running a transaction, right? What happens if a message gets delayed, right? Just because it's TCP IP, it doesn't mean it'll guarantee within the stream it's going to come in the right order. But like, there might be some weird network hiccup, and your message to one node for one stream might get delayed and then show up like a second later. Or what if the other node doesn't physically crash, but it's running a Java database system, and then the garbage collector runs, and it pauses for like 5 seconds, which can happen. So now that system looks unavailable, but it's still alive. You can ping it. You can ping the node. It's still going to be responsive, but the database server process itself is not responsive. What do you do? And then what happens if we don't want to wait for everyone to agree that we're going to commit a transaction, and we send back responses early? Okay, well, now what happens if one of those nodes again crashes and comes back? How do we account for that? So this I just want to reemphasize that this is very, very hard to do. And this is why you don't want your random JavaScript programmer building these kind of things. This is what you want to use a database system to do this for you. And when we see vector clocks, it gets even worse if you let JavaScript programmers handle that. All right, so for today's lecture, we're going to make a very, very important assumption. And that is, we're going to assume that all the nodes in our distributed database system are friendly, or we control them, or they're in the same administrative domain, right? That means the software itself will be well behaved. Now, there could be problems, like I said, the JVMs could kick in and start doing garbage collection and pause your node. But again, it's not like we're worried about a hacker coming in and running malicious code on our database node, right? So that means if one node tells another node, let's commit a transaction, and that node says, yep, let's commit it, I agree, let's do it, it's not going to reverse that decision later on purpose, right? Failures is again, a different thing, we'll handle that, right? So if you don't trust the other nodes, then the protocol you're going to need is not what we're talking about today. You're going to need what is called a Byzantine fault tolerant, or BFT protocol. And this is basically how blockchains work. Right? Blockchains are going to run transactions. It's basically a database. They're going to run commit, but they're not going to trust the other nodes. So they're going to have this BFT protocol to be able to handle that, where nodes can start lying and doing things that you don't want them to do. So don't do this unless you're doing Bitcoin, right? We don't want this anywhere near any of our OLTP database systems, right? Because the performance overhead for this is like 5 to 10x over what the protocols we'll talk about today. It's bad enough we got to send network messages potentially over the wide area network, and now we're dealing with the speed of light. But then you got some protocol here because you're worried about Bitcoin miners and stuff like that. We're not going to do this. And most applications, unless you're money laundering through Bitcoin, you don't need this. Okay? This is clear. So it always comes up like, okay, why are we doing this? How we handle this if we want to can we just do blockchain instead of doing all the stuff we're doing? No, blockchain is going to be a degenerative case of what we're talking about today, and slower. Okay? So assume, again, all our nodes are friendly. We wrote the software. We're running the software. We control it. We don't expect them to do malicious things, but we still need to account for failures and anomalies. All right, so first thing we have to talk about is how we're going to replicate the database across multiple nodes. And then that'll lead us to discussions, okay, how do we extend or propagate changes between these nodes to keep things replicated? Then now comes to the question of, okay, now we have a bunch of replicas, we've told them to do a bunch of stuff. Can we get everyone to agree that those changes are allowed to happen and in the right order? And then we'll finish up talking about the consistency issues we have to deal with under the CAP theorem or the Paselic extension to CAP theorem, okay? All right. So the first thing we want to do is replicate our database. So now maybe thinking this doesn't sound like a distributed database, where I'm just saying, okay, I have a node, a primary, a bunch of replicas. That's a distributed database, right? It's a simplistic form of it because we'll see in a second, because you're just having all your writes going to one location, but you still need to propagate them, and you still need everyone to agree that those are the changes you want to propagate. I would say for the basic non-partition replication scheme we'll talk about today, like 99% of the people out there, this is what you'd want to use, right? Because you want to use this for scalability, be able to have run extra queries, but you also want this for durability or availability, right? Because the primary could go down and you can fail over to a replica. We'll see the multi-primary in a second. So this is going to be independent of what we're talking about here today, of whether we're doing partition or non-partitioned databases. I mean, does every node have a complete copy of the database, or do they have some partition of it? And also whether we're doing shared nothing or shared disk. Because shared disk systems like Aurora, they're basically going to be doing the same kind of replication stuff we're talking about here, but they're going to do this underneath the covers for you and hide it from you. So the question is going to be, how do we configure our replicas? Like, where do the writes go? Where can reads go? When do changes actually occur? Right? How do we wait for those changes to be acknowledged from other nodes? And then what happens when we have to do, how do we actually want to update the database? Do we run queries or do we replay the log? So again, this is basically a brain dump of all these different design decisions, and we'll just go through one by one and you understand the trade-offs between them. All right, so the first issue is what the configuration of the system is going to look like when we have replicas. And as I said, the most common one is going to be the primary replica. And sometimes this is called leader-follower. In the old days, it used to be called master-slave. So if you want to look up older papers on this, they'll refer to it master-slave. There's a lot of documentation using that terminology. So you might have to use that term to find what you need. So the idea here is that there would be some node in our system, in our distributed system, our distributed data system, that we're going to anoint or elect as the primary. And then all writes have to go to that primary. And then it's the primary's responsibility to then propagate those changes to the the replica nodes, or the followers. And so if you ever want a consistent view of the database, you can always go directly to, or in the latest version of the database, you always go directly to the primary, because all your writes are going there. If things get committed there, you'll see them right away. But you can offload read-only transactions and read-only queries to the replicas, and that takes some of the load off of the primary, so it can just try to do the writes as fast as possible, and then you can do the reads on the replicas. Now again, you may not get the latest version of the database on the read replicas, but for some applications, that's probably okay. Right? Now the key thing we're going to have to deal with, and we'll see how to handle this in a second when we talk about consensus protocols, is at some point the primary will go down. Either by accident, like someone trips over the power cord, or there's a software hardware failure, but oftentimes too when there's a version upgrade. Like Amazon will force you to upgrade your versions of your database every so often. And so at that point you have to restart the server. So at some point the primary is going to not be is going to go down, and you have to elect a new primary from one of the replicas. So we'll see how to handle that in a second. The second configuration scheme is to do what's called multi-primary, sometimes called multi-home. And this is where any transaction can update any data object on any possible node. And now the replicas have to synchronize between them when these changes occur to make sure to figure out who's allowed to actually commit, who's actually should be the correct version of the database, of an object. So let's look at two visual examples. So the first one is primary replica. So again, you have the primary, all your write queries have to go here, but then you also could send read queries as well, read transactions. And then in the background, the primary is going to be able to send messages to the replicas to apply the changes that occur on the primary to the replicas. And we'll see it in a second. This either could be basically the write, actually the most common one is the write-ahead logs that we talked about before. So remember, we talked about when the change data capture, where you could have all your updates occur on one node, and then you have this other component or tool that looks at the write-ahead log you're writing out to disk, and also can send those write-ahead messages out to another node. That you would use that for this. So now the replicas are basically in kind of this pseudo recovery mode, where they're getting these write-ahead log messages over the wire, over the network from the primary, and just replays them and applies the changes as if it was doing recovery like normally. But it's like it's an infinite size, or it's a never-ending log file, right? Because it's not at some point you're going to reach the end like in Aries and say, okay, I'm done. Now I can start running transactions. You're kind of constantly always applying the changes as the primary sends them over. So the primary will always have, again, the latest version of the database. If you want to read the latest version of the database, then you have to send your read queries here. But you could also send read queries to the replicas. And again, you would do this to offload the work that the primary would have to do. So then maybe the primary just only does writes, which again, which are expensive because you have to update indexes, you have to generate write-ahead log messages, right? You have to run whatever the transaction protocol or the current control scheme you need, right? And then so if I want to have I want to avoid my primary doing a bunch of work for my read queries, I can send the read queries to the replicas. Most workloads are read heavy, right? Maybe like 1% of the queries or 1% of the transactions are updating, 99% of them are reads. Just think how you browse the web. It's usually the case. The other scheme is to do multi-primary. And this is where you can do reads and writes to any possible node. And then now when a transaction goes and commits, now I have to figure out what should be the correct version of this, right? So again, we can use that write-ahead log scheme that we talked about before. We're propagating updates between the different nodes. You could have multi-tiers of a hierarchy, like where you have, say these are two different data centers. You would have one leader within a data center that gets all the updates and knows how to propagate them to a bunch of followers that it has locally, right? But in general, again, there has to be some process to figure out who's allowed to commit what changes if two writes occur to the same object on different nodes. So most systems are going to need this. It's only the really, really large guys need something like this. Like this is what Facebook uses, right? Actually, Facebook started off with this, right? And the problem is, of course, that when Facebook became this global thing, this is, over 10 years ago, if now I'm down in Brazil, their data center is up in California, if I do a write to my timeline or whatever it's called, when you post like a stupid cat video, right? That post would have to go up from Brazil to the California data center, do the write there. But now if I click refresh on my timeline, I may not be able to, the change may not be propagated down to the replica down in Brazil, so I may see a stale version. Of course, now people get pissed, like, where's my cat video I just posted? So Facebook will play this little trick where they would actually put a cookie in your browser that recorded your timeline post, so that when you refresh your page, it would read the local browser copy to see your post and show it back to you, right? Even though it actually hadn't been propagated to the database yet. So you can do that when everything's in the browser for some applications, but as you start doing more different kinds of services and different kind of application types, they had to switch over to something like this. So this is what they do now. Google Spanner will be like multi-primary, right? But again, most distributed databases only need to be the primary replica. All right, so the next thing we have to consider is how many copies of data should we maintain at all time to make sure our database is still available. And I'll cover what I mean by available when we talk about the CAP theorem in a second. The basic idea here is that it's a threshold to determine, we assume nodes are going to go down. How many nodes are we allowed to go down, or how many copies of our data are allowed to go down before we say we don't want to allow any more reads and writes, because we don't want to take a change from a transaction, modify an object on the last copy of the data we have, then that node crashes and we come back, and now all our replicas that we had before don't have that copy. So in the database world, this is called case safety. In the distributed systems world, it might be called something different. It's basically just to say, again, at what point or how many copies I must have before I start I halt operations. And we'll see in the case of when we talk about the CAP theorem again, the NoSQL guys would allow this to go below a majority, Whereas in the sort of relational distributed database world, we don't want to lose data. So we're very, very careful about setting this threshold to a number that says, okay, once we go below this number, then we just halt the system. And so that makes it unavailable, but that's better than, some people would argue that for some applications, not being available is better than losing data. All right, so now the question is also going to be, how do we actually propagate the changes from either from the primary to replicas or between the multi-home systems or the multi-primary systems? And this is where this consistency stuff, when I talked about ACID before, I said, oh, it's kind of hand wavy when it's on a single node. Now this actually should make more sense when you do this in a distributed system. So the idea is then when a transaction says I want to commit, at what point do I send an acknowledgement back to tell them that they've committed? Again, assuming I need to replicate the change across multiple nodes, do I wait for all those replicas to acknowledge that they got the change? Do I wait for none of them? Or do I wait for some of them? So the two extremes are you wait for none of them and you wait for some of them. Or sorry, wait for none of them and wait for all of them. If you wait for all of them, that's called strong consistency. So that means no matter what, if I'm told a transaction is committed, no matter what node I then go to, I'll see the changes of that transaction reflected. In eventual consistency, the idea is I won't wait for all my nodes, my replicas to say I got the change. I'll immediately come back and say, yeah, I got it. But now if another query tries to go read data on another node that hasn't applied the change from the primary, I might not see that change from that transaction that is committed, even though I was told it was committed. So eventual consistency, the idea is that you're not going to wait for the nodes to acknowledge it. They'll eventually get updated. So basically it looks like this. So assuming we have a really simple setup, we have a primary and a replica. And then all the writes go to the primary. We tell the primary we want to go ahead and commit. And so then we propagate the change to our replica, and we tell it go ahead and flush. Right? We'll talk about how it's actually staging the updates in the write-head log in a second, but assume that it's got all the changes at this point, and now we say go ahead and flush. As if it was a transaction being run directly on the replica by an application. It's like the primary is telling it, I want to run this transaction, go ahead and commit it. So we got to make sure we flush all the changes because, again, it's all the buffer pool stuff we talked about before, right? It's the steal no force, where you have to flush all the write-head log changes to say our transaction has committed. So that means the primary has to stall and wait. We send the flush message and it has to wait, and then at some point it does the flush, sends back the acknowledgement, and then at that point we can then tell the application our transaction has committed. Asynchronous commit or eventual consistency basically says, I go ahead and tell commit. I go tell the replica node, go ahead and flush this as well, but I don't wait for them to respond. I don't need to. And I immediately send back an acknowledgement. Now again, this node may crash, and then this one gets elected as the new primary, so I may come back here and actually, now my transaction is missing because maybe this message didn't actually make it over. You typically send the flush message first, then you send back the acknowledgement. But if you did it in the order, right, if you send back the acknowledgement, then send the flush may never make it, right? And now that transaction the replica doesn't know what was the fate of the transaction. You saw this last class when we talked about consistent hashing, right? We talked about quorum writes. So that's somewhere in the middle where I do a write to commit my transaction. My data is replicated 3 times. But I have to wait for 2 out of 3 nodes to acknowledge that they flushed the data. Then I send back the acknowledgement. Right? The idea is that, again, if you assume that failures are rare, what's the likelihood that this thing's going to, one of these guys is going to crash? It's pretty low. Or maybe they're both immediately going to crash at the same time. Potentially pretty low. So rather than paying this penalty to wait, I'll immediately get back my response. Again, we'll see how this fits into the CAP theorem in a second. So most systems, the NoSQL guys are going to be down here doing some kind of version of eventual consistency. The sort of classic distributed relational database systems like a DB2, an Oracle, nonstop SQL, those guys at the top, they're going to be doing synchronous commit because they don't want to lose any of your data. All right, the next question is, when do we actually propagate the changes from the primary to the replica? And again, it doesn't matter whether you're doing shared disk or shared nothing. It doesn't matter whether they're doing multi-home versus or multi-primary versus a single primary. If you do continuous propagation, that means as the primary is getting, or one of the nodes is getting all the changes from a transaction, it's immediately sending out the write-ahead log messages, the log messages to the replicas as soon as those queries get executed. Right? Think of it's like, again, the write-ahead log. I'm putting my write-ahead my log entries into my buffer that eventually get flushed to disk. But as soon as I generate a log record, I'll also immediately send that out over the network. I can still batch it up, maybe with other messages, but I'm not waiting to acknowledge or not waiting for a commit message. I'm just sending those things over the wire. The downside of this approach is that I have to also then send a commit message, which is fine. But if I send an abort message, then my replicas may have been applying a bunch of changes, only to later find out that the transaction didn't commit successfully, and they have to roll back the changes. If you do the propagation on commit, then basically you stage all the log records that you have on the primary, and only when you know the transaction is going to successfully commit, then you ship that over to the replica. And now this guarantees that it only sees transactions that has committed, and you don't have to waste time rolling things back. Aborts are typically rare in most systems. Right? Think how often, again, you browsing the web or using your bank website or something, how often do you abort things? It's not that often. So the top one is always going to be better because you don't have to wait to know whether a transaction is committed because you assume it's going to commit and you send your log messages as soon as you get them. Okay? All right, this last one can be a bit confusing, so bear with me. And please ask questions if you're confused. So it's been kind of hand-wavy in PowerPoint showing arrows from one node to the other without really saying what are we actually sending along, right? But for the most part, you can assume that we've been sending write-ahead log messages. So that means that when we run a transaction, the queries are running on one node. They're making changes to the database, and then we're sending the write-ahead log messages for them to get applied to the replicas. This is known as active-passive scheme. And the idea is that the transaction is actively executing on one node, and then the other replicas are passively applying the changes that the transaction made on the node where it was actively running. But it doesn't have to be this way. I could actually run the transaction in multiple locations, let them run independently, make whatever changes that they want. I don't have to send any write-ahead log messages between them, right? The only thing I need to do is at the very end when the transaction commits, just everyone says, did you commit? Yeah, I committed. Done. Right? So this is called active-active because the transaction is actively running in two different locations at the same time. And depending on what queries they're doing, they can run independently without coordinating between each other as they're running. So again, the only message they need to send at the end is, did you complete successfully? Yes, I did too. So this only works if you can guarantee that the transactions are deterministic. All right, so how do you do that? Well, if I have a random call in a SQL query, then I just make sure they have the same seed on both nodes. That covers that. What if they call now? I try to get a timestamp with the current time. Okay, well, I just make sure that you set the transaction timestamp to be the same when they both start. All right, so then now how do you keep the clocks coordinated? That's kind of hard, but so maybe the transaction shows up at a centralized system. You assign it a random seed. You assign it a timestamp when it starts, and then you send it to the two different nodes to execute simultaneously. Yes.
So you save on communication because you don't have to do it only in one and pass the data, but then don't you at the end still have to make sure that all nodes have the same data? So what are you really saving here?
Yes. The statement is, and he's correct, is that since I still have to, at the end when the transaction commits, since I have to just make sure that I still have to make sure at the end that everybody's committed successfully, So there's still a network round trip for that. What am I actually saving? It's the intermediate data I'm sending along, which could be a lot, right? I could update 1 billion records in my transaction, and I got to send 1 billion write-ahead log messages over the network to propagate those changes. I avoid all that. Yes?
So when here we say need to check at the end whether the transaction ends up with the same result at each replica, do we mean doing some work upfront in the design of the database such that any transaction will be deterministic, or check at the end of each transaction and actually send something between the replicas?
Right. So he's for the second statement here, I'm saying need to check at the end whether a transaction ends up with the same result at each replica. Is this something I'm doing at the application level to make sure my transactions are all deterministic, or should the database system provide this guarantee for me? It's the latter. So you would have to have a system that can guarantee that you have the same ordering, serial ordering, if you will, of transactions on both same nodes, and that anytime there is non-determinism in the queries, like a random call, like a timestamp, that you guarantee that both all the copies of wherever that transaction is running will see the exact same thing. Almost very, very few systems actually can do this. The only one, at least I can think of, is VoltDB, which is based on a system called HStore, which I helped build. There might be a few others, but you typically would see this in a system where you execute transactions as store procedures, which we haven't talked about. But think of a store procedure as like an RPC call you can make to the database system that has all your application logic, things you can't normally have in SQL, like if clauses, for loops, exceptions. Right? You could have procedural logic, imperative code that you run in the database system as a function call, intermixed with a bunch of SQL queries. And so again, now instead of sending these back and forth between the queries, because the timing can get off between the client and the server, I just say, run this transaction for me. It looks up in the catalog, gets this function, just runs it beginning to end. And again, avoiding any non-determinism in those functions, you're guaranteed to end up with the same state. Yes?
How is active passive different from primary replica as shown on the slides? Because from what I understand, the active is mainly like the primary that actively execute, and replica is just receiving the updates from write-ahead log.
Actually, the question is, I'm saying this is not the same as primary replica versus multi-primary. I just mean this like you could have, you could still have you still could do an active-active scheme with primary replica, but instead of me shipping the write-ahead log to you, I'm just telling you, here's the transaction I'm about to execute, you execute it too. And as long as you come back and say, yep, I did it and got the same result you did, and result is the state of the database that we care about. And the reason why VoltDB can do this is because they run all transactions in serializable ordering. Their execution engine is actually single-threaded. So I can have a single-threaded engine per CPU core, but now all I need to do is I specify the order of the transactions when they arrive, and think of like it's a batch of store procedures I need to execute. As long as both nodes execute them in the same order, I end up with the same state. So most systems are going to do active-passive because it's going to build off the write-ahead log infrastructure we talked about before that we already have in our system, and it's just easier to, again, to put the replicas into recovery mode, or just have the ability to replay a write-ahead log message that's coming over the network instead of coming from a file. Yes.
So active is gonna always be like higher lows for like each node compared to active passive, right?
So active is always going to be higher lows. What do you mean?
I mean like workload. If you like, you're basically doing like the same query, running the same query over every node that you have to replica. Instead of like, say if I have like two transactions, two requests, I could have like, if it's multi-primary, I could have like compute one in one node and compute the other one in another node. But if you do like active, you have to do two like in both.
Yes.
Nodes, right?
So his statement is, it may be the case that the amount of work you have to do in active would be more than you'd have to do under active-passive. Again, it's a cop-out, but it depends. right? So I could have a query where it does an update and sets some value, a equals a plus 1. But I don't have a where clause. I have a billion tuples. I got to scan. If I do active, then every node has to do that billion record scan to find the record it needs to update and apply that one change. But under active passive, I do the scan on one node, then I send the log record for that one record I found I need to update. That then gets applied, right? But again, assume you're doing that synchronous commit, or where I can only send the write ahead log message and I have to wait for get it applied. I got to scan the billion records, then send the one log message to get applied, and wait for that to get acknowledged and come back to me. Whereas if everybody's doing it independently, yes, that may take a long time for that one particular query. But when they're done, it's just like, hey, you did it? Yep, we're good, we're done. Like it's not multiple round trips back and forth. And then there may be another case where the query is super simple, but I do a billion updates and I got to send billion log records. Again, you can come up with different examples for all these where one's better than another. From an engineering perspective, this is going to be better because this is just relying on the write ahead log infrastructure we already have. And to be honest, most applications don't run as stored procedures, and most applications will have non-determinism in them. Once you start bringing in lower isolation levels too, then the problem is if you're doing active, if I can run at different isolation levels, then depending what other transactions are running at the same time I'm running, I may get different results on different nodes. And it's super hard to do. Nobody does it because it's not worth it. All right, cool. I think we get the gist of this. This is good. And again, almost every system is going to be doing active passive. Okay, so now, if only one node has to decide whether a transaction is allowed to commit, then making that decision is easy. Even under this precludes primary replica setups, right? Because under primary replica, you have to, the primary say, I want to commit, but you got to wait till everyone else to say, yeah, we can go ahead and commit this too. Did they apply the replica? The replicas applied the changes. So if you're running on a single box, committing transaction is still hard because we have to do all the concurrent stuff we talked about before, but at least the node can reason about what's going on in its own purview, in its own system. Things are much harder, I can't emphasize this enough, when we have to bring in multiple nodes to decide whether a transaction is allowed to commit. Because first of all, how do we get everyone to agree that a transaction is allowed to commit and get notified about that agreement? And then what happens if now we try to go commit the transaction, get everyone to agree, and then one of the nodes goes down, or the primary goes down? And then now you need to elect a new primary, right? So how do you handle that? So the main takeaway from this is the same decision it takes to say whether a transaction is allowed to commit is actually going to be the same decision about who's allowed to be the primary. It's just another transaction, but slightly different semantics. So this is what is called an atomic commit protocol. In the database world, you call this atomic commit protocol. In the distributed systems world, you call this a consensus protocol or atomic consensus protocol. But at a high level, they're basically doing the same thing. And the idea is that we want to be able to decide the order in which transactions are allowed to commit across our different nodes. So again, if you take a distributed systems class, they talk about these state machines, like in Paxos. It's basically the same thing, because the state of the database is defined by the order in which transactions commit, including transactions that are not allowed to commit. In the state machine replica, I don't know what example in distributed systems, I don't know what example they always use, like a simple counter, like who's allowed to increment the counter or whatever. It's the same thing. The commit order of our transactions is determined by the state of this the distributed system. And again, we're going to have to do this no matter whether our database is partitioned or replicated or not. We want to get everyone to agree that a transaction is allowed to commit before we acknowledge to the outside world that it has successfully committed. So there's a handful of protocols that can do this. We're going to focus on these two here, two-phase commit and Paxos, because these are the most common ones used in distributed databases. Although Raft is probably more common than Paxos at this point, but it's a simplified version of Paxos. And so I'll discuss Paxos in a simplified way that basically is the same thing as Raft, right? There's a minor difference. So two-phase commit was first written about by, or it was always sort of assigned or attributed to Jim Gray, the guy that invented two-phase locking and inertial stuff we talked about before, because he has a paper in the 1970s that mentions it. But then Jim Gray actually refers to some Italian guy that designed the first two-phase commit protocol for the Italian version of retirement system, a social security system in the 1970s, right? But that Italian guy says he didn't invent it either. It's basically the same thing we use in the old days of contract law, right? So this is actually taking something we do in the real world and applying it to a distributed database system. So two-phase commit came first. Stonebreaker came along and did three-phase commit because they're trying to overcome this property of if a node goes down, you have to pause the system. So three-phase commit was an attempt to try to deal with that problem, but it didn't. Nobody does this because it's complicated and doesn't handle the corner cases. There was a four-phase commit from Microsoft. They do that because they're running on hardware accelerated or they're using RDMA with like InfiniBand stuff. We could ignore that. ViewStamp replication came out in 1988. And again, this was done in the distributed systems world. And then the one everybody knows about is Paxos. So ViewStamp replication is by Barbara Liskov. She won the Turing Award a few years ago. And then Leslie Lamport did Paxos, but he didn't know about ViewStamp replication, so I don't think he cites her. ZAB is from Zookeeper. It's the Zookeeper Atomic Broadcast Protocol, or Broadcast Protocol. Only Zookeeper uses it, but it does exist. And then RAF came out of Stanford. It's supposed to be a simplified version of Paxos, right? So for ViewStamp replication, I think that was the one that was first proved to be correct under all possible failures. And then the only system that I know that does ViewStamp replication is a thing called Tiger Beetle. It's a distributed OTP data system out of South Africa. But again, most systems are going to use Paxos or Raft. So at a high level, all these atomic protocols are basically doing the same thing. And there's this great paper we'll mention in a second from Jim Gray and Leslie Lamport that basically assess the state of the world for all these atomic protocols and sort of try to distill down what they have in common and what's essentially what they're all trying to do. So at a high level, the idea is that these notion of these resource managers, I've been using the word term node, but basically there's something that can control or can determine the fate of data in our database system. And so that now when a transaction wants to commit across these resource managers, we have to go through these series of steps to determine, is this thing allowed to commit, yes or no? Right? And so the idea is the basic state machine of any protocol is that when we start off in the working phase, we're applying changes to the database. At any point, if any of the resource managers, any of the nodes decide this thing is not going the way I want to go, I'm going to go ahead and abort it. Then you immediately go into the abort phase. Right? As soon as one node or one resource manager says this thing is not allowed to commit, that's game over. That thing has to go down. The transaction has to fail. Then at some point, the transaction's work is done, and you enter the prepared phase where you say, you're trying to get everyone to agree, is this thing allowed to commit or not? If no, you go to abort it. If yes, then you're successfully committed. So for any commit protocol we want for our distributed database system, we want to have these two important properties. First is that the protocol has to be stable, meaning that once we decide this transaction is allowed to commit, and everyone agrees, at least, well, as long as the majority agrees in Paxos, but in two-phase commit, everyone has to agree. It has to be unanimous. But once we decide this thing's allowed to commit, you can't reverse that change. Right? That's what the blockchain guys are trying to avoid that problem, where people rolling back changes or changing their minds. In our world, we don't worry about that. And then we need to guarantee that our protocol is consistent, meaning at some point, at some undetermined point, that everyone's going to agree that this is the correct state of the database. And again, for our world, the state is the order in which transactions are committed. We're also going to want to assume that that our protocol will provide some guarantee of liveness, and that just means that no matter what, there's some way to keep the system moving forward, the state machine moving forward, and try to make some progress. Doesn't mean it's going to be efficient, but at least we're going to at least not be stuck in a state where we can't get out of and can't commit new transactions, right? And the guarantee to achieve this basically says at some point we need to be alive. The nodes need to be alive and communicating with other nodes to make forward progress on this. So the first protocol we'll discuss is two-phase commit. We'll see what the issues with this are and some optimizations we can do, and then we'll see how Paxos can handle them. And so the main takeaway is going to be, again, two-phase commit came first, Paxos came later, but two-phase commit is actually a subset of Paxos, or a degenerate case of Paxos. And again, this paper from Leslie Lamport and Jim Gray basically proves that, shows that they're actually the same thing. But the Paxos has a different requirement for deciding when their transaction is allowed to commit. So we have an application server, we have a bunch of nodes, right? And without determining how we decide that this one is the node that's going to be the one we want to talk to commit a transaction, we're going to go to this node 1 first. So under the parlance for two-phase commit, the node that's in charge of deciding whether a transaction is allowed to commit is called the coordinator. And then all the other nodes that are going to be involved in this committing this transaction will be called the participant. Paxos will use different terms, right? But they're basically the same thing. So now, the first phase of two-phase commit is to send a prepare message to all the nodes. And that's basically where they do whatever checks that they need to do to say, okay, we're about to commit this transaction. Is this allowed to happen, yes or no? And then if each node, looking at its own context about what the transaction did on its local node, because it doesn't know what it did on the other ones potentially, it can then decide, yes, this is allowed to happen. I'm going to go ahead and commit. Or I send that acknowledgement, okay, that we're okay with preparing this thing for committing. Now, I'm not showing this in the PowerPoint slide, but for all these messages I'm sending out, all the messages I'm receiving and all the messages I'm sending out, those are going to be another write-ahead log messages I'm going to maintain. And then when I want to go ahead and commit, I have to flush all my network messages that involved in two-phase commit out the disk so that if I crash and come back, I can know where I was in the two-phase commit protocol when I was running a transaction. And you can just put in the same write-ahead log you put for your regular queries. So now, once the coordinator gets all the acknowledgments from every node that's a participant, because it has to know which ones it needs to talk to, all right? It may not be all the nodes in my distributed database, but it's the nodes that are involved in this transaction. Once they all agree, I get all the OK messages, then I enter the second phase where I said, OK, to all the other nodes, go ahead and commit this transaction. Same thing, each node goes ahead and applies the changes. If I care about synchronous commits, then I'll flush the changes and wait till the flush finishes before I send back acknowledgement, but I don't have to. And then now these come back, I'll send OK. And at this point here, the node can then respond to the application and say, now your transaction has successfully committed. All right? So again, the key thing in two-phase commit is you have to wait. The coordinator has to wait for everyone to come back and everyone to agree to say this transaction is allowed to commit.
Question.
Yes?
How will a participant node know it's okay to send the OK back for prepare message? And what is the criteria?
His question is how would a participant decide on its own whether a transaction is allowed to go ahead and successfully commit? It's just all the stuff we talked about when we were running on single node anyway. So say you're doing OCC, right? And you then enter the validation phase because you got the commit message. I may, if I'm doing forward validation, my write set may intersect with the transaction that's already running, and therefore I can't commit, right? If it's two-phase locking, if you hold the locks and you completed all the updates, it's fine. Well, it depends on when you check for integrity constraint violations. So in some systems, you can say, go ahead and apply all my changes, but only check the indexes to see whether I have a duplicate key when I go ahead and commit. Then you would fail this. You would fail that. So it depends. But it wouldn't be because because you did something on node 2 and then node 3 did something different. Because you're not talking to node 2. You're just looking at your own system, your own node. Right? So the abort case is basically what he's asking about. So node 1, the coordinator sends a prepare message. Say for whatever reason, node 3 decides this transaction cannot commit. No, we can't happen. We can't let this happen. So they send back the abort message. And then no matter what node 2 thinks is allowed to happen, as soon as we get one abort message, the game's over. This transaction has to abort. So we immediately enter the second phase where we tell everyone to go ahead and abort. We don't have to wait for the acknowledgement for the second phase from all the participants before we tell the application your transaction has aborted. Right? Because as soon as we get 1, we know the transaction is never going to commit, so we immediately can return back to the client. Okay. So this is repeating what I just said, right? So each node is going to record the inbound and outbound messages into some kind of write-ahead log or non-volatile storage. And then now when you crash and come back, depending on whether you're the coordinator or participant, you can do different things, again, depending on how far you got into the two-phase commit protocol, right? So if I was a participant and I crashed after sending back the OK on the prepare message, when I come back online, I look at my log, I say, oh, I sent out an OK for this prepare message. Let me go figure out what actually was the final outcome of this transaction. So you would go back to the coordinator and say, hey, remember transaction 123? I said it was going to be OK to commit. Did it actually commit? And depending on the on what the coordinator comes back with, you could either reverse the transaction, which you would have all its changes because it's in your write-ahead log, or you could you could apply them and say the transaction is actually successfully committed. If you never got through the prepared phase, then you just abort the transaction. Like if I was getting a bunch of updates and then my node goes down, that's essentially the same thing as aborting the transaction. So no matter what, the transaction will abort. So if everyone was saying, let's go ahead and commit this, and you're the coordinator and you go down, then when you come back online, if you do come back online, then you would send a message to all the nodes and say, yes, we go ahead and committed this. Even though you may have not told the outside world your transaction has committed, again, under the transaction protocol, the transaction guarantees of a data system, if we successfully save all the changes to disk, but don't send the commit or acknowledgement back to the client before we crash, the transaction is still considered as committed. So now it's up for the application server to say, go back and do a lookup and say, did the thing I just sent you actually get committed or not? All right, so I said a lot of this already, but like, what happens if the coordinator crashes? Well, the participants can decide amongst themselves what to do after some amount of timeout. Right, so typically there'll be like a heartbeat message you're sending around between the different nodes to say, are you awake? Yes, I am. And at some point, the heartbeat messages don't come back. So eventually you'll time out and just say, okay, well, this thing is, we have to decide whether, did you tell the coordinator we're going to go to commit? Yes or no? And then if everyone says yes, then you can decide again whether you want to commit the transaction. But the key thing about this is that the system will not be available while you're trying to figure this out, because you can't commit any other transactions while you're trying to figure out whether the current transaction you're at is allowed to commit or not. Right? Because what happens if that other transaction read something from this first transaction, but then the first transaction ends up being aborted, but we've already told the second transaction is allowed to commit. And that would violate asset guarantees. All right, if a participant crashes, then the coordinator is just going to assume that it sent an abort message. Right? If you don't get that first prepare OK back from the participant, you assume that it's going to fail no matter what. So you go ahead and tell everyone the transaction has aborted. So there are two optimizations you can do for two-phase commit. One is very common, one is not so common. The first one is called early prepared voting. The basic idea is that if you know that if you know that when you send a query request to a node in the system, that this is the last query you're ever going to execute for this transaction on this node, and you're never going to come back to it with another query, then you just piggyback in the message and say, hey, run this query for me, give me back the result, and oh, by the way, also send back me your vote for the prepare phase. So you get back the query result and you get back either an OK or an abort message. So then now when you run two-phase commit, you don't have to wait for that round trip again between the coordinator to the participant, because you already know whether it's going to commit or not from that last query. Most systems don't do this because you don't have a way through SQL to know where the query is actually going to run in the first place. So how would you know that this is going to be the last query you may send? I think JDBC, you may be able to send a flag say this is the last query for this transaction. I know in other systems, in VoltDB you can do this, but most of the time you can't do this. What is more common is to do early acknowledgement after prepare, where instead of waiting, once you get past the prepare phase, you get OKs from all the participants, instead of waiting for them to say, okay, did you commit, yes or no, which at that point, again, once you pass the prepare phase, that transaction is committing, no matter whether the notes go down or not. So instead of waiting for them to all acknowledge that yes, we went ahead and committed, you immediately shove the acknowledgement back to the client, because you assume the window between the time when the client the flush and you send back the acknowledgement will be small, and you have a recovery protocol anyway to deal with if one of the nodes crashes during the commit process, right? You assume it's going to go ahead and commit, so you can send the commit message back right away. And this is very common. So basically, I get the application server, they submit a commit request. Node 1 sends the prepare phase messages to all the different nodes, or the coordinator sends the prepare message to all the participants. They all say, yep, good, yes, we can go ahead and commit this. And then immediately, once you get back all the OKs from the participants, then you can shove back the commit response, the success message to the client. But then you still have to run the rest of the two-phase commit protocol. Right, so you're just cutting off one round trip from, you're cutting off one round trip, waiting for one round trip on the commit message. You still have to do it, but just you don't have to wait for it. Yes.
What if the coordinator crashes right after sending success before phase 2?
His question is, what if we're here, we get prepare okay from all the participants, and then we send back success, now we crash, which node crashes?
The coordinator.
So he said, what happens if the node coordinator crashes? Okay, well, as I said before, the participants will have a heartbeat message that it eventually will time out. You're not hearing back from the coordinator. You told her you want to commit this transaction. You can't commit any other transactions until you figure out whether this transaction is committed, right? So at some point you time out. So then you need a way to say, okay, well, who else is in my cluster? Oh, node 3 knows about node 2. So they start talking to each other and say, hey, you remember transaction 1, 2, 3? Did you say it was allowed to commit? Yeah, I did. Did you say it was allowed to commit? Yes. And then you go ahead and apply that, record that they successfully committed. Or before you time out, the coordinator comes back online, right? Saw that you got the OK messages out, saw you sent the success messages out, and said, okay, let me just make sure I tell these guys, if they haven't figured it out yet, make sure they know the commit. This is hard, right? There's a lot of these corner cases you got to deal with. Yes?
Could you say again why we need a OK message for the commit?
His question is, why do I still need this phase here?
No, the OK response.
This. Like, why do I need this OK from everyone?
Yeah.
His question is, why do I have to wait? If I send a commit message to everyone, why do I have to wait for the response back and say, yes, I went ahead and committed? So it's basically for that you know that everyone has successfully applied the change, and therefore, when I go ahead and now commit the next transaction, I know that everyone's in sync.
So let's say in this case, if I send the success back to the application, and there is another request from the application, but at the same time, I didn't receive all the OK from the participant, does that mean I can't start the next transaction?
So you could start it, you just can't commit it. So they have another commit message shows up, right? So you send back success. You haven't gone through the commit phase yet. Another commit request shows up. What do? Well, you would know that you're still trying to finish off the first transaction. So you can't start committing the second transaction until you get back for everyone to acknowledge that they successfully applied the changes. Because you don't want the case of like, if I don't do the second phase, right, these guys don't know whether this thing's actually committed yet because they don't know that everyone voted OK. Right? So they're waiting to find out whether the transaction they just ran is actually going to commit or not. Right? So now I do this. Now I say, okay, guys, we all agree to commit. Guess what? They've committed. Great. So at this point here, all of the node 2 and node 3, they can actually begin the process of committing another transaction. But this guy still can't because he doesn't know that everyone has acknowledged that they have successfully applied the changes from this transaction. Because I asked him, I asked him to commit. I don't know whether that message actually showed up yet. And it's only when I get back to the acknowledgement and then I know that they applied the changes I told them to apply. So now when I commit the next transaction, I know that transaction, if it read anything from the first transaction, it will see the correct version of those records. Okay. We have 13 minutes left. Let's go through the hardest protocol in distributed systems in that time, right? But Paxos, again, it's going to be a degenerative case. Two-phase commit is going to be a degenerative case of Paxos. So if you understand two-phase commit, again, I'm going to simplify it so you'll see that how it just maps into the same ideas. And all the things we care about under two-phase commit, we still care about in Paxos, right? So again, this is the provably resilient protocol, atomic commit protocol in the face of asynchronous networks. So it's basically going to be the same thing under two-phase commit where we have a coordinator telling the world, I want to commit this transaction. But under two-phase commit, you had to get everyone to agree that this thing was allowed to commit. Under Paxos, you just have to have a majority of the nodes agree that something's allowed to commit. Right? Again, now you see why two-phase commit is a degenerative case. The original Paxos paper, actually, who here has read it? What do you think of it? He's shaking his head no. It's crazy.
I'm glad we have a Paxos made simple.
Actually, Paxos made simple is not good either, right?
What's that?
It's not. All right. Go read this paper. Just go spend 5 minutes looking at it. It's crazy. It's the best paper ever, but in terms of like its prose, it's not a traditional computer science paper. It's written as if he's an archaeologist finding this ancient voting system from this tribe on the island of Paxos in ancient Greece, right? That has nothing to do with computers. This is how they vote by throwing tablets into a hole, and you come back and read later on what was thrown in the hole, right? It's brilliant. It's amazing. But like if you try to take this paper and say, let me go implement this, not going to happen, right? So the story goes, he wrote it in '89, submitted it to a distributed systems conference, and it got rejected, right? And if you go to Leslie Lamport's website, he has like this chronological history of all the papers, like what he was doing, where he was living, who he was dating, what he was eating, like for every single paper. So he talks about in this Paxos paper, the part-time parliament, about how it was a genius paper, it was a work of art, and those idiots on the reviewing committee, they didn't know how to appreciate it, right? So when I was in grad school, I was assigned to present this paper in my distributed systems class. And I basically said the same Lamport said. Like, this paper's, it's a genius, a work of art. And those reviewers, they were stupid. They didn't know what they were doing. The professor was Morlise Hurley, who used to be here at CMU, and now he's at Brown. He was actually one of the reviewers of this paper. And he said that the story goes is like they were originally okay with this Greek archaeology metaphor. All they asked him was put in the appendix a proof to show that like how, what this thing was actually doing of the algorithm. And Leslie Lamport basically said, this is a work of art, I'm not making any change. So he got rejected. So then he puts it, the story goes, he puts it in his filing cabinet, forgot about it, saw all these papers in the 90s where people were sort of dancing around the corners and kind of getting close to what Paxos had already implemented, but wasn't solving the complete problem. So then he pulled it out, dusted it off, then resubmitted it. And then there's a prologue here that talks about how like, it was this mission was recently discovered behind a filing cabinet of the editorial office. Despite its age, the editor-in-chief felt that it was worth publishing. So like they dug it out and got it accepted or got it published. Then he pointed out there's a follow-up paper from Leslie Lamport called Paxos Made Simple. That doesn't help either. The best paper to read to understand Paxos is the Paxos Made Live from Google. That one describes how my opinion, that's the best description of it, at least in the modern papers. That came out in 2004, 2003, right? So again, and then there's this other paper from Leslie Lamport and Jim Gray. This came out in, 2006, right before Jim Gray disappeared at sea. Does everyone know that story? Jim Gray won the 21 database in the 1990s. He was sailing his boat in the San Francisco Bay in like 2006 to dump his mother's ashes, and he went to a part you normally don't sail to by yourself, and then his boat disappeared, right? And they never found him. They didn't find any sign of him. He got declared dead, I think, a few years later. But like, to give you an idea how important Jim Gray was and how much he meant to a lot of people, this is early days of like crowdsourcing. They actually moved satellites in space to go over San Francisco Bay and take pictures of it. And it was an early crowdsourcing effort where people would like look at pictures of the ocean or the bay and try to find his boat, right? And they never found it. So, anyway, so this is one of the last papers that Jim Gray wrote with, before he disappeared. It's kind of a heavy way to start this, but let's go to it. All right, so Paxos, what is it? Okay, you have a commit request from the application server. Instead of calling these coordinated participants, Paxos is going to call these proposer and acceptors. There's a third node type in Paxos called learners. We can ignore that. It's basically someone who doesn't participate in voting, but can see the changes and update things. Think of like a non-voting replica. Right, so we send this proposed message out to everyone. Right? Say for whatever reason, acceptor node 3 dies during this process. Just like two-phase commit, they all agree that this thing wants to go ahead and commit. And as long as we get a majority back, not all of them, just a majority from all our acceptors, then the transaction is considered committed. Then we do the second phase and tell them to commit. Right? And then they all send back acknowledgments. At some later point, if the acceptor wakes up, then he can learn from the other nodes what happened with this transaction to get up to speed. Right? So in Raft, they're going to call these, I think they call it still proposers and acceptors. I think the learners, they call followers. It's, again, they're all basically doing the same thing. But another way to think about this, to guarantee the liveness property we talked about before, we can always still make forward progress. Under two-phase commit, if we crash, if a node goes down in the middle of a commit process, they got to figure out, they got to figure out what was the state of that transaction, and then decide what to do. Again, the system is unavailable during this time because you're trying to figure out whether a transaction is allowed to commit or not. In Paxos, you don't have that problem because proposers can keep proposing new stuff, and you still, there's still things are moving forward. So say along this timeline here, we have a proposer over here. He's got 3 acceptors, and there's another proposer on the other side. So he says, all right, I want to commit this transaction, so let me go ahead and propose that this is commit n, right? How they came out with this timestamp or this number, it doesn't matter. All the acceptors say, great, fantastic, yes, we know about this transaction. We agree to go ahead and commit transaction in order n. But then now, say this other proposer comes along and is unaware that this is the first proposer, and they propose to commit n plus 1. Soon as you see a new proposal to commit a transaction, any previous uncommitted transactions have to abort. Because you always have to accept new proposals and always keep marching forward at a time, right? In two-phase commit, you have to wait until the first transaction commits before you can propose to commit another transaction. So now, all the acceptors see n plus 1. They haven't acknowledged that they're going to commit it. As soon as they see it, that's enough to say that anything came before that it's aborted. So now when the first proposer comes back and says, I want to go ahead and commit this transaction, you guys told me it was a good idea or not, then they come back and say, I want to reject this. And tell it, you're telling us to commit transaction n, we just saw n plus 1, you're no good to us, come back again. Right? So then they all agree to commit n plus 1, they commit, the first proposer says to go ahead and commit it, they send back the acknowledgement and we're good to go, and then this guy can then propose to commit the transaction again, or abort it entirely. So obviously this would be very inefficient if you have a bunch of nodes in your system all proposing to commit transactions and just clobbering each other. Like the system will be live, you can accept new things, but you're never going to commit anything because transactions are going to keep getting aborted and over again. And so this is what Google put together in this paper I mentioned about Paxos Made Live, and they put the idea called multi-Paxos. And basically, the idea is that you only have one node get anointed as the leader in a sort of Paxos group, and then they're the only ones that's allowed to commit transactions. And if you have this, you can just skip the propose phase because no other node is going to come along and try to propose and commit a new transaction. If now, though, if one of the nodes goes down, you fall back to the regular Paxos protocol. So to handle the case where the leader may go down, and the system obviously it would grind to a halt, you set a lease or a timeout for how long they can be the leader. And then when that timeout it finishes off, you run a leader election, which is just another round of Paxos to decide who's allowed to be the new leader. And then now you basically introduce incremental back off, where if I try to say I want to be the new leader and I can't get it, then I'll sleep for a random amount of time, and then maybe somebody else will be able to sneak in and get it before I do. Again, the nodes aren't malicious. If I can't be the leader, it's not the end of the world for me. Right? If you're the leader, that's fantastic. We can commit transactions together. It's beautiful. Right? So how to set the timeout depends on the system. Right? The longer it is, the less time you have to spend doing these leader elections. But now the longer you may have to wait to time out on something because the leader has failed. Again, the heartbeats can maybe pick that up earlier, but it could depend on how often you're sending those. So in Google Spanner, these leases are 10 seconds, I think, they say in the paper. Yugabyte is 2 seconds. CockroachDB, I think the default is 5 minutes. TiDB is 10 seconds because they just follow Google, right? It depends on, depends on the environment you're running in and the expectations of the nodes. All right. So quickly, two-phase commit versus Paxos versus Raft. Again, two-phase commit is going to be all transactions at the block if the coordinator fails after the prepare message is sent until the coordinator comes back, or you then figure out, amongst the nodes themselves who's allowed to commit. Paxos is non-blocking as long as the majority of the participants are alive, and provided that you can keep going without continued failures. Raft is the same thing as Paxos, but there's fewer node types. There's basically just participant and acceptor, which I think they call follower. And then when they do a leader election, rather than letting anybody be the leader, you have to have this requirement that basically says only the nodes that have the most up-to-date log is allowed to become the leader. So if someone is falling behind, you don't want them to become the leader because obviously they're slow and going to make things worse for you. So if you have the freshest data or the freshest commit record of all the transactions, then you're allowed to go ahead and commit. All right, let me blaze through CAP theorem. Again, I think this should be, again, if you take a distributed systems class, this should be pretty should be aware of this already. But we can touch this up next class to refresh people. All right, so CAP theorem, this was proposed in the late 1990s by Eric Brewer at Google, or he was at, it was some web startup. Basically, they recognized that, if you have a distributed system, well, again, that's what a distributed database is, that it's impossible to have three properties. You can't guarantee to be always consistent, always available, and still handle any time there's a network partition. So the real way to think about the CAP theorem is basically, are you going to be a consistent system or an available system anytime there's a network failure? Right? It doesn't make sense to be a consistent, available system and when there's network partitions or network failures, communication failures, because that doesn't really make sense. It really has to do with what do you do when there's a failure. So consistency just means what we talked about before, right? The idea is that if I make a change on one node, say I have a copy of my database, I apply the change here, I should then apply the change also on my replica. Once I do that, then I can tell the outside world this transaction is successfully committed. Now if anybody comes along and tries to read that value on another node, they'll see the correct version. Right? Availability just means that if a node goes down, again, assuming it's a simple primary replica, then I can have any transaction run on this node, get back any changes, and the other node on the other side of the network, assuming we still can communicate, can go ahead and read data over here, right? That's fine. So the database is still available even though some of them are going down. The hard one is network partitions, right? Say my network gets severed. Now the two nodes can't communicate with each other. So what's going to happen? So again, assuming I'm a primary replica, this primary can't talk to its replica anymore. It says, okay, no big deal, I'm the primary. This replica says, I can't talk to the primary anymore. Well, guess what? I'm now the primary, right? I'm only showing two nodes. You would do basically, a leader election between all the replicas on each side. But this guy says, yep, I'm the primary too, because it doesn't know that this guy's still alive because it can't talk to him. So now the problem's going to be, both these guys think they're the primary. You don't know about the other one because you can't talk to them because the network's down. So the first transaction modifies A. The second transaction over there modifies A. They both get acknowledgement, say that your transaction has committed. Now the network comes back up, and you got to reconcile these changes. They both thought they were primary. They both thought these changes were allowed to happen. But now you have conflicting values. So this issue here, when you have the network failure and you can't communicate, this is called split brain. Right? Both sides of your brain can't communicate each other, but they both can operate independently. So again, the question is, what do you do when this happens? If you care about consistency, then you basically would halt the system. You'd halt the system when you don't have the majority of the nodes. Right? And then this means that when the network comes back up, now the node that the portion of the network that had the majority of the nodes, it maybe got a bunch of updates, and you now propagate those updates to the replicas, but at no point do you deal with conflicting values. So again, most distributed relational data systems will choose the first one. The second one is you allow the split to happen, you allow the writes to occur on both sides, or however sides you have. Then when the network comes back, you got to do a little magic to figure out what should be the correct version of those values that got modified. So you can either let the server do this or let the client do this. If the server does this, then it's just last update wins. Like whatever had the newest timestamp, that's the latest version. Good enough. Right? So Cassandra does what most systems do. Most of the NoSQL systems do. The other approach is to do what's called vector clocks. This is actually invented by Leslie Lamport. It's basically multi-versioning as we did before. We keep track of, like, here's the version of a value, a version of an object at this timestamp. And it's like you have a list. So now when I go read a value, go get A, instead of getting one value, I get back a list of values with different timestamps. And now my application code, I got to figure out which one should I care about, which one is the correct one. And maybe go ahead and apply the changes. I only know one system that actually did this. It's called React. And it was a nightmare. Because again, your average JavaScript programmer isn't going to know what the hell a vector clock is, isn't going to know how to reason about if I update two things and now they both have different timestamps because one got modified and one did get modified by another side, which is the correct version. You're basically repeating the logic to figure out what is the correct version of multi-version currency control in JavaScript. That's not going to go well. Don't do this. Okay. So I'll just say there's an extension to CAP theorem called PASELIC that came out in 2010. It's basically, if there's a failure, again, do the same thing. Are you partition tolerant? With partition, are you always available or consistent? But on a normal operation, you got to make this trade-off between latency and consistency. It basically says, if I have a primary, I do my update in one data center, I got to propagate the changes to the other data center. The question is, how long should I wait for to acknowledge it? Because I can wait an infinite amount of time, and I'll guarantee to be consistent, right? Eventually, I'll get responses back, but then now the system's not available, right? Or maybe I only wait for one of the updates to come back, and then I can send back the acknowledgement. So there's this trade-off between how long do I want to wait versus how quickly I can respond to things. All right, so hopefully again you recognize how hard this is, and I'm sorry for going over. Google was one of the first systems that said, "Hey, we don't want to do transactions because we want to be web scale." They did this in Bigtable, and a bunch of systems copied what Google did. But while everyone was recreating what Google did in the open source world, Google said, "Wait a minute, looks like transactions are a good idea." They hadn't published it yet, but they've been working on a system called Spanner for a long time. So everyone else was riding the NoSQL wagon, NoSQL wave. Google was actually building a real system, Spanner. They didn't support SQL first; that came later. But they had this nice little snippet in here, and it's basically saying what I said before. We believe it's better to have applications programmers, aka JavaScript programmers, deal with performance problems due to overuse of transactions rather than always coding around the lack of transactions, meaning deal with vector clocks and inconsistent data. So it basically says you have some really smart people like you guys spend time making transactions run fast on your distributed database and let everyone else deal with that. And make them better programmers. Okay? All right, sorry for going over. Have a good break. Monday next class, distributed OLAP systems. See ya.
I need something refreshing when I get finished manifesting. Too cold, a whole bowl like Smith & Wesson. One quart and my thoughts hip-hop related. Write a rhyme and my pen's intoxicated. Lyrics are quicker with a sip of more liquor. Since I'm a city slicker, brain waves are quicker. Rhymes I create rotate at a rate too quick to duplicate. Feel a breeze as I skate. Mics at Fahrenheit when I hold it real tight. Then I'm in flight, then we ignite. Blood starts to boil, I heat up the party for you. Let my girl rub me and my mic down with oil. Record still turns with third degree burn from one man. I heat up your brain, give it a suntan. So just cool, let the temperature rise. To cool it off with same odds.